Hey guys, today I'm going to talk through day 2 of the binomial random variables with you. This is really going to build off of what we did on the first day of binomial random variables. First thing, recap from the reading, these are the two new formulas for binomial. You can only use these formulas for binomial random variables, and how you know something is binomial by checking bins, and that's what we discussed last class. The next thing I want to point out from the reading is just this new 10% condition. So you can find more info on page 114 in your reading. The binomial distribution, it makes a good approximation as long as you're not sampling more than 10% of the population. So you have to make sure that your samples satisfy this 10% condition. To go through the examples real quick, I'm just going to give you the answers. You can ask any questions that you might have on them on Friday. For the first one, you should have C. Next is D. 3 would be D. The next one would be D. And the next one would be C. And I know those are misnumbered. That should be example 4 and example 5. Okay, so next is the teamwork. So I'd like for you guys to pause the video and try to work through some of this together and then replay the video to kind of talk through each of the problems. Okay, so reading through the first example, we're talking about a stats class. They're talking about an activity on page 340 in the textbook. If you want to look it up, you're more than welcome. But basically, it's just about students being able to tell the difference between tap water and bottled water. And each of them have a 1/3 chance of correctly identifying the different type of water just by guessing. X is going to represent our number of students who correctly identify the cup containing the different type of water. The first task you have is to explain why X is binomial. This is when you check bins. So you want to go through the process and determine if it's binary. So is there a success? So yes, our success is the correct identification of the water, which means the failure is incorrectly doing that. I, your independence, one student's result is not going to tell us anything about another student. N is our set number of trials. So we had 21 students, so it happened 21 times. And then S is standing for our probability for each success. So each kid, no matter what, is going to have a 1/3 chance of guessing correctly. So therefore, this is a binomial random variable because it's counting the number of successes in this setting. So, of the 21 students in the class, 13 made correct identifications. Are we convinced that Mr. Bullard's Mr. Bullard's students could tell bottled water from tap water? Justify your answer. So here's what we're going to do. We are actually going to find the probability of getting more or equal to 13 correct identifications, and that will give us that probability. So I'm going to talk through the calculator speed because this is probably going to be your easiest process through this. So since I want a more than, that means it's a complement because in a binomial CDF, it's going to calculate cumulatively. So it's going to be the value you plug in and everything prior to. So I'm going to do 1 minus, and I'm going to set my number of trials. Notice that everything's labeled. My probability of success is 1/3, and my value is 12. Since I want to find the probability of getting 13 correct identifications or more, that gives me the probability of 0.0068. So are we convinced? So the students had less than a 1% chance of getting so many right if they just guessed, because that's what they told us. This is just by guessing. So this is strong evidence that some of the students in the class could actually tell bottled water from tap water because the chance of guessing and getting it right was so low. Next, find the mean and standard deviation and then interpret each value in context. So this is using our new formulas. So if we look and find the mean, this is when we're going to take our probability times our number of trials. So our number of trials is 21 times 1/3 gives us 7. So that means we can expect about 1/3 of his 21 students, about 7 students, to guess correctly. To find the standard deviation, again, you're going to plug into this formula. So N is the number of trials. P is your probability of success. This is representing the complement, so the probability of failure, so 1 minus the 1/3. And you get a standard deviation of 2.16. In context, this is if the activity was repeated many times with students in groups of 21 who were just guessing, the number of correct identifications would differ from our mean of 7 by an average of 2.16. Okay, the last one to talk through, we're talking about an airline finished training 25 first officers, 15 were male and 10 female, and they want to become captains. Unfortunately, only 8 positions are available. The airline managers decide to use a lottery to determine which pilots will fill the positions. Of the 8 captains chosen, 5 of them were female and only 3 were male. First, we have to explain why the probability that 5 female pilots are chosen in a fair lottery is not this calculation. The reason that this is not the calculation is because once you choose someone, they don't get put back into the pot, basically. So if I am chosen as a captain, I don't go back into the running of becoming captain number 2 because I've already been chosen. So that's called sampling without replacement. This is a 0.4 chance that me as the first pilot would be selected. However, then that's going to change the probability for the next female pilot to be chosen. So this non-replacement is significant because we are taking a sample that is larger than 10% of our population, so 8 out of our 25. For number 2, it says find the actual probability that 5 female pilots are chosen and compare. So what we're looking at, think of these 25 officers like sitting in a bowl, like their names on a piece of paper or something. It's lottery method, so you just pull one out. So we are trying to find the probability that 5 female pilots are chosen. They don't specify an order, so we're just going with it that maybe our first 5. I think that's how I have it written out here. So the probability that we get exactly 5 females is our 8 choose 5 because we have to consider every combination, and no matter when they're chosen, whether it be first, second, third through the fifth, or if it's first, the third, the fifth, the tenth, whoever it might be, or excuse me, the eighth, the probability is going to end up being the same because it's multiplication. So we need our 8 choose 5. This is representing 10 out of 25. So there's 25 people to start with, and this first person chosen, since we're using 10, that's representing a female. Then we've got 9 out of 24 because we are assuming this first person chosen was female. So therefore, our pot goes down, so how many people we're choosing from, and our female total goes down. So that same thing happens until we get 5 females. And then we still have a smaller pot because 5 females were removed from our total 25 first officers. But now we're getting 3 males because that's what actually happened according to our problem. So that's why we go to 15, 14, and 13, and then we find that that probability is 0.106. Okay, that's all I have for you guys, so you can work on your worksheet packet. I have left the rubrics on the little side table next to my desk. They are kind of grouped already for you, so please make sure to pick those up so that you have them, and I will see you on Friday. Have a great day.